Hello, this is Snuffleupagus from Brisbane, Australia.
Our performance is based off an episode of the children's television show Sesame Street. In our modified episode, Cookie Monster Ngonga bakes a batch of cookies. Cookie Monster needs to recognize which objects are needed for the recipe and which aren't. He realizes that we don't have any eggs, so the chicken dances and lays one he can use.
Sophia and Aoife worked on electrical, and Zandy, Annabelle and Jocelyn worked on mechanical, and everyone contributed to software.
The camera is using machine learning to identify the different objects. Multiple methods were tried, including cuddle segmentation, using teachable machines, and various versions of TensorFlow. We found that using a model trained by Edge Impulse with their dedicated library worked the best. The model takes hundreds of images of each item to detect, then feeds it into a neural network to complete the transfer learning. The detected ingredient is then sent to the Arduino to continue the performance.
Originally, we designed laser cut plates. However, they were too unstable and had a high chance of snapping. So, we ended up using the brackets that came with the ARM kit with longer and redesigned 3D printed linking pieces. We continued using the given brackets due to the stability of the metal, which was needed to keep the arm intact. We also designed 3D printed shoulder joints in order to hold the arm in place to the humanoid.
The arm is programmed using an OpenCR board, which is similar to an Arduino. The servo motors are daisy-chained and programmed with the Open Manipulator library. Arrays with positions are fed to the arm to move the servos. The movements were tuned so objects can be effectively manipulated without collisions.
The Bluetooth chips, HC05, used in each of the robots, send signals using the serial ports on the Arduino. These signals will create a connection between the 4 robots. Gongo is the master and the slaves are the Cookie Monster, the chicken, and the NeoPixel. This communication between the master and the slaves will allow the robots to communicate with one another, so that each robot will start on time as soon as the other robot ends their movement. The implementation of the Bluetooth in this performance means that each robot will align with the performance. Bluetooth module sends a signal to the other one, and the other one sends one back, and this will send a signal for the NeoPixel to change.
The bases are important to allow the robots to move freely and accurately without affecting balance. The chicken drive system is an Omni base with 2 laser cut plates, standoffs, and Omni wheels. The humanoid bases have 2 regular wheels and motors with 2 swivel wheels at the back. We made the base large so that the top-heavy humanoids are more stable. The humanoid structure is made of mostly recycled materials. Wooden boards are held up with metal poles and cross-bracing for stability. Metal clamps hold the poles upright and keep shells from falling. The mouths were constructed from foam and have a servo motor and a string to open and close the jaw to imitate speaking. The humanoids have different functions for each dive movement. An inertial measurement unit, or IMU, was implemented to prevent inconsistent movements. The IMU corrects the robot if it gets crooked when going straight and allows turning to a specific angle. The mouths use random positions and speeds for the talking illusion. The chicken includes fusion-designed laser-cut plates held by standoffs and aluminium poles. The bottom plate has a cut-out space with a servo motor that moves a flap, allowing the egg to drop. Once the egg is released, Gongo is alerted via Bluetooth.
The 3 main robots all use the same custom printed circuit board, or PCB. It includes both surface-mounted and through-hole components to maximize space and efficiency. There was a shield for the Arduino Mega, voltage regulation system, and pinouts for various components. The motor controllers installed on the board could not supply the current required for the motors, so external L298 boards were used instead.
The MP3 module uses software serial to set up communication between the module and the Arduino, which replaces the communication pins. There are different audio files for Cookie Monster that we've edited and put onto an SD card that's attached to the MP3 module. It has a 3.5mm jack that's outputted to the speaker.
Today, all cooking cookies. We need eggs.
For the display, we use the 32x8 flexible NeoPixel matrix. In coding this, we use libraries relative to the matrix, such as Adafruit Neo Matrix, which allowed scrolling text. It had several commands necessary, such as identifying banner width, starting position, and gap spacing. This was coded using an Arduino Uno and had a high level of current necessary. For example, at 100% brightness and white light setting, it would need 15 amps. We circumvented this issue by not using certain high-powered colors and setting the brightness low.
We use the QTR sensor for the chicken like a color sensor, using the numbers that it outputs as the 2 different colors. Lower numbers from this sensor will be used for the white mat, and the numbers above 800 will be used for the black line. This means that the chicken will always stay within the mat.
We chose our 4 main features based off what was absolutely vital in our performance. The camera allows the robots to interact with their environment, the arm allows them to manipulate objects, the Bluetooth to communicate, and the drive bases to move around the space. These are also among the most complex and challenging technologies we implemented. Without any of these features, our performance would not run.
Thank you for watching our technical demonstration video. We hope you enjoy our performance.